Okay, so here's where I promised we do a little bit of a whiteboard lecture on RLC. But before we even get started, I just want to remind you, or what I have been for a while, and keeping it simple, and realize that we're really doing nothing new here with regards to circuit analysis in this last half of the course, other than the understanding that when it comes to determining our voltages, our currents, and our impedance, that it's involving reactance. So we have the imaginary components of imaginary voltage, imaginary current, imaginary power, and imaginary opposition coming from the reactance of a coil or a capacitor. So the first thing I'm going to look at is RLC series. And if we look at RLC series, well, we're going to have an AC source connected to a resistor, a coil, and a capacitor, or RLC. And the first thing we need to understand is something we've always talked about, and that is when it comes to current in this circuit, I total is going to equal the values of all the current. We know that current is our common quantity when it comes to series, so that's going to equal IR, equal IL, and equal IC. So if we were to then choose, and remember, we can choose any point in a circuit as reference, so we can choose any quantity as reference for an AC circuit as well. And let's just assume or start, and let's say that our current is going to be our reference here as our common quantity. So we're going to put I total at 0 degrees here as reference. Now don't forget that I total value is the same value of current for all components. Okay? So if we want to determine the total impedance from this circuit, it means that we're simply going to add the values up. But we need to remember, when we add the values up, there's values that are imaginary here. So that means that our Z total value is going to equal R plus a plus J XL plus a minus J XC. Right? Our equation will be R plus JXL plus minus JXC. So what does that look like if we look at it as far as the phasors that represent this opposition? We're going to have R at 0 degrees as our real value of opposition. We're going to have our XL as our plus J component of imaginary opposition coming from the reactance or the magnetic field of that coil. And we're going to have an XC as a minus J value. Okay? Well, when you look at this part of the equation, what it means is when you have a plus 90 value added to a minus 90 value, if the minus 90 value is greater than the plus 90 value, obviously you're going to have a net result that is minus 90 degrees or minus J. I think you get the idea. This part of the equation is representing the two quantities that are 180 degrees out of phase, and you have a net reactive value. So let's suppose that in this case XL was the greater value. If we look at this impedance triangle, XL, or the plus J, would be greater than the minus J. So when you added the minus J value to XL, you'd end up with some net value down here. Now this is the result of adding a minus J XC into this, right? So as a result, you end up with a net XL value, and that would put your Z total, that would put your Z total right here as far as your total impedance. That was when XL was greater than XC. So when you added the minus J, you ended up with a net value here. That puts Z total here. Notice how this provides your angle of impedance, phi or phi. this comes from a primarily inductive circuit because we have XL as the greater value. We know it's primarily inductive. So if that's the case, that would have to mean that Eli is describing the voltage and current relationship from this impedance triangle. Sure enough, you know by Ohm's law that if you divide a positive value of impedance into a applied voltage at 0 degrees, you get a lagging current. So sure enough, Eli does apply to that relationship. And of course, what happens if we have a minus J component greater than a plus J component? That means you would add the plus J component here, and your net value, remember this would be the result of plus JXL being added to this minus J value. You would have a net reactive value of what you see here, and therefore the Z total value would be found here as Z total. This would be your angle of impedance, phi or phi, and when you divided that lagging impedance into the applied voltage, Ohm's law would give you a leading current, right? And if it's a leading current, that means that ICE is going to describe the voltage current relationship. And sure enough, lagging impedance, leading current. Leading current is what we see from that acronym. So what would the voltage triangle look like then? Well, it means that every value here that was used to determine the total impedance, every value here would be multiplied by the I total value, right? So if it's multiplied by the I total value, that's the same quantity being multiplied by each one of these oppositions. And so it means the voltage triangle is going to look exactly like the impedance triangle in terms of all the proportions, right? Because they're multiplied by the same value. So if we were to look at the voltage triangle here and use I total as the reference. So let's just do that for a moment here. And what we're going to do is realize that for E total, or total source voltage here, ES is going to equal our VR plus, now remember that's a plus J component multiplied by I total, so it's simply going to be a plus J VL value added onto I total times minus J, minus J VC value to give us our total voltage. So if we were to look at this circuit, again, if we ended up having a VL value greater than a VC value, we would have a primarily VL circuit. So our VL net value would be a plus J value in our voltage triangle. If we had a VC value greater than our VL value, we would have a VC net value as a minus J, and that's going to determine our overall voltage triangle, proving Kirchhoff's voltage law. Okay, now remember, one of these voltages is always in phase with the current, and that's going to be our VR. So wherever our VR value is at 0 degrees, in phase with our total current. And let's suppose now that we have a VL value greater than our VC value. That's going to put our E source value here as the total of VR plus VL equals E source. What are we going to have right here? This is going to be our circuit phase angle, right? So whatever angle we have here is going to indicate how many degrees the current lags the voltage. And remember, up here, Eli has to be the case, doesn't it? Eli has to describe that relationship, and sure enough it does. So quickly, VC greater than VL, that means that we're going to have E source down here. This is going to equal angle theta, and if we use the applied voltage as the reference and describe the relationship between voltage and current, If E source is the reference, that's now saying that our current leads that voltage. And as a result, you're verifying that ICE is the acronym that describes the voltage current. Okay? So remember, even though we have the total current here in this diagram as our reference at 0 degrees and showing the applied voltage with respect to it, we can change that up after we've completed all this triangle and say E source is now the reference and where is current with respect to our applied voltage. And the applied voltage is very common in power systems as a reference. So we have leading current, ICE is indicating the relationship. We have lagging current here. This is E source as a reference. That's a lagging current. Lagging, this one's leading. And we've got Eli describing this relationship, ICE describing that. And that's our way of using Eli and ICE to say we've drawn our triangles correctly, we've got the right representations of plus J minus J, because we can see that that's clearly supported by those two acronyms. So that's essentially a summary of RLC, and this is the process you use in solving RLC series, is to go through impedance, then take impedance into voltage, understand the current is all the same, and then lastly we'll be involving power in our next presentation.